This meeting is being recorded.
Holy moly. Justin, why, if I tap, your computer must be different than mine. All right, I just wanted to hide the little thing.
Oh, yeah, no.
Can we start, or should we? Are we good? Hello? Okay, cool. All right, hi everyone. So this was the model eval group where we wanted to try to make it an easier process for someone to, provide any given model output in a certain format and pull different SnowEx field data to start evaluating your model and get a better idea of are you underestimating, is your model good, is bad, whatever. So the two main data sets or tools that we were using here was that same snow model output that we talked about yesterday during the modeling tutorial. And then we accessed a lot of different field data sets and airborne data sets straight from that the SnowEx database. A note, sorry, the formatting got a little funky, but a note on the model data. We're using this specific model format, but we're trying to set it up where it can be a little bit more generalizable, where if someone wants to upload their own model output that's in the same format, they would also be able to take this notebook and run with it. I don't know.
All right, so like Melissa said, we wanted to make this as generalizable of a process as possible so that you can kind of plug and play, more modular approach. And what we found is that when we went towards actually accessing the data that we were going to compare versus our model, we were kind of duplicating efforts a lot. So as we were going along, we also had folks following behind, and we made this toolbox that we're calling Data IO Funcs. And just to kind of give you a general idea of what that looks like, we have a bunch of outside functions compiled in this toolbox as shown here that has that you can point to and actually use those functions in a way that's really simple and straightforward. So for instance, in this toolbox itself, we have a access list, which accesses the model data. We'll kind of go through these as we go along. There's a class called access SnowEx, and within access SnowEx, we have point data, layer data. In development, we'd really like to include, it shouldn't be point data and layer data, it should be point data and image data. But we're also would like to include a layer data in there, just ran out of time. And right now we're focusing on a static date and grabbing dates from around it, but it would also be nice to do this to add functionality for a time series comparison as well. The hope is to be with this sort of toolbox at our disposal. We want to be able to provide, say, a configuration file or maybe just a single cell of a notebook with all the information that it needs and just let a user go, essentially. So this is kind of what it could look like. What I'm showing here is a bunch of parameters for the list data acquisition. So, where it is, the variables we're interested in, the model resolution, how we're going to resample it. We can do this, for the SnowEx data acquisition parameters too. And then we have this, this range of filters that are potentially applicable for all our data. We're talking about what data are we looking at, the lat-long boundaries, and the buffers on either side of our focus state that we want to pull data from. So for the purpose of this demonstration, we wanted to focus on a small subset. Oh, I will actually pass this over. How about that? Sorry.
Good. Yeah, so then we also created an interactive map so that you can kind of visualize the latitude and longitude range that you've inputted. Let me zoom in a little here so you can actually see it. Sorry, zoomed out a little too much here. All right, so here is the subset of Grand Mesa that we're working with. And this is a really great tool because it allows you to really quickly identify if you've entered the wrong latitude and longitude. And it also gives you an idea of the geography of the area you're working with. So if you take a look here, you can see that in the left side of our subregion, there's a reservoir that's going to really impact our model output. And you can also see there's a reservoir up here a little bit. And so as we take a look down, here's a satellite image of our study site. And you can see that this reservoir is on the left here. And you'll also see when you look at our results how that impacts our results.
Yeah, so hopefully, we have an easy way to find your location. And we're going to focus on this demonstration on February 8th, 2020, because we have a lot of overlapping data, as I'm sure all of you are aware of. One thing I really wanted to plug really quick is that in our development, we actually included a new package. It's called XESMF. And this is a Earth system modeling framework. This is very common with a lot of models that don't necessarily run on a gridded framework. So what I mean by this is that you may have model output that's rectilinear or curvilinear, where you don't have a grid of latitude, a grid of longitude, and a rectangular coordinate system to work with. You instead have something that maybe conforms to actually the Earth's curvature a little bit more. But that is difficult when you come down to actually using your data, because you need to be able to have it in a projection that and sort of spatial reference that Python actually recognizes. So we used XESMF, so I'd really recommend taking a look at it. But to access our list data, we kind of did these 3 steps within this toolbox that I discussed above. You first access the data from the S3 bucket. You subset it using the time indexing, and then the domain lat, lon bounds. And then we specify the lat lon values that we want XESMF to regrid to and reproject using a user-defined sampling method. So, going through all this, it's pretty simple. It all happens in this function right here. And output from that, you can see from our model perspective, is kind of shown here in X-array format. So something that you should be able to use right away, provided just a few simple parameters.
And this portion of Toolbox takes us to the SnowEx database. We are pulling the field measurements, and we use the tutorial from earlier this week on access and query of the SnowEx data. This particular portion pulls snow depth point data, and you can see the range of dates. They were specified, the date was specified earlier, and so we had plus minus 2 dates. And we were able to get 68,533 point snow depth measurements for our comparison. And next is LiDAR data, I think, the raster data.
Okay. So yeah, we've heard before how LiDAR or airborne LiDAR can be is considered an important snow data set due to its accuracy in measuring snow depth on the ground. And so this data set we could use to evaluate or validate numerical snow prediction models such as this that Melissa or Justin talked about, or any other numerical prediction, snow prediction models. So we derived the LiDAR data from the SnowEx database for the date for 1 day for Grand Mesa, and I think the function to derive it is here, right? The link to the function is here, and I just want to show the output. So this is the comparison for LiDAR, what LiDAR shows versus what the model shows. The first plot is the LiDAR in the native resolution or the 3-meter resolution, where you can see that it's really fine scale. You can see a lot of variation in the snow depth. in this Grand Mesa bounding box area. And the second plot is the LiDAR that we changed to or downscaled, not sorry, downscaled, upscaled it to the model's resolution, which is the 100 meter. And now you can see that it's a little more homogeneous or a little more coarse. So the variation in the snow depth is less. And within that, it's a little hard to see, but within that, there are like patches of data shown here. Those are point data from GPR and snow pits, and you can comparatively see how they differ from one another. And the striking difference you can see is like on the third plot, where the background plot is from the model. So you can see how the model is like just one color. So it's more homogeneous versus the LiDAR, which is more heterogeneous. And you can see like in the LiDAR plots on the upper left side, the white spaces, those are the lakes that you could identify from the one that Valerie showed earlier in our bounding plot. Over here where you can see like those two lakes here in the map, which is also easily identified or shown in the LiDAR maps, but not in the model, the numerical model data. And this graph here, plot here shows the difference between the model data and the LiDAR data. And you can see that the color, the map here is more towards the red, showing that the model is more negatively biased for snow depth. So the actual snow depth shown by LiDAR is higher, and the model data shows that the snow depth is, model has less snow depth than the actual what LiDAR is showing. And this one here is just the similar thing to show the difference between the snow depth. In the first one is the LiDAR in native resolution versus the plot. And you can see like, how the data is distributed. And the second box is for regridded LiDAR or the coarser LiDAR versus the point. And it's, you can see the box has moved down a bit, showing that, moving to the coarser resolution, the LiDAR is now more on the negative side of the box. And the third one is the list versus the point, and the list is the most negatively biased compared to what's on the ground. So it's kind of like kind of makes sense that as you go coarser, it's more homogeneous, or the heterogeneity is lost. And going back to Justin.
Yeah, I'll just finish out here, but well, we found some interesting results from this. In model world, obviously Grand Mesa is interesting because it's so flat. And even at 100-meter resolution, we're not seeing a lot of topography for it really to resolve differences in precipitation. Even a model that does wind redistribution like snow model may not actually resolve the drift due to differences in elevation at 100 meters. So there's a lot of really cool things to look at here. The last thing we did is we just really took those points and looked at them at a point-by-point scale. So here what I'm showing is the point snow depth observation versus the snow depth as defined from these three products that immediately overlay. As you would expect, we see a pretty good regression for the LiDAR. But then, as we coarsen, we see, these sort of vertical stripes where you're constrained with how much variability you can represent. And then, we could also do this a different way where we take and average all the points that fall within a certain grid cell. That's what I'm showing here. And we see, once again, far too little heterogeneity in our model as compared to, say, a regridded LiDAR. So, a lot of really interesting initial results. And we hope that some of the tools that we developed here can be used right away to help people access and manipulate and visualize data, but we also think this is like a really great starting point potentially for further work to kind of develop this toolbox and make data I/O just a lot more accessible and easy going forward. So yeah, like I said, we have a lot of directions we could possibly take this, but I wanted to finish with a huge thanks to the Hack Week organizers and all the friends that we have here, both old and new. So I think that's all we have.
Any questions? Do you need, what type of credentials do you need to access like a list bucket that it's in? Is it NASA funded researchers, anyone? Private or government employees?
Yeah.
Or?
Great question. So right now it's open to everyone. I don't know how long that will stay open. I can definitely chat with our IT folks and let you know. If you are interested in sample data of some sort, just let me know and I can figure out how we can share it. Maybe we can work on a better model simulation. This was one that was done really quickly for the Hack Week. But yeah, if anyone's interested in sample data, maybe just over Grand Mesa, that's probably small enough to easily share. So just email me. I'm happy to help however I can.
Did you find the model resulting in any differences in the forest areas or?
If you,
So when we scroll back up to these images, I'm pretty certain that the right side of the bottom plot, which is the model, that's where some forests were. So you can see there are some differences there. But the rest of this particular subset is so homogeneous. We were saying that this really highlights the need for better metadata. This is forest width NLS2, which is a 14 by 14 kilometer grid cell. So this whole little study area that we zoomed in probably has one precipitation point forcing the whole area. So even though we're running at fine spatial resolution, we're still limited by our forcing data. And I think this, oh sweet, thanks Justin. I think this does a nice job highlighting, like it's not just about getting our models better, it's about getting our forcing data better as well.
We need to work with the atmosphere.
Yeah, exactly.
All right, thank you. Next we have space station.